Okay, as we mentioned yesterday, uh, in a previous lesson, we're going to be needing to be talking about antennas. Antennas actually warranted their entire own separate lesson. So, some of the things we want to be talking about in the antennas in this lesson is we're going to talk about decibels. We've always seen decibels written dB, but what does it mean? So we're going to look at that. We're going to look at why we have to have an antenna, which we kind of talked about a little bit yesterday. The different types of antennas, shapes, sizes, their designs, their applications. We're going to look at signal strength and direction, and we're going to look how antennas actually work and do their job. So far, we've looked at the properties of radio frequency signals, most of the components that are required to generate the signals, and how to modulate the RF signals with some kind of meaningful information to be transmitted, whether analog like music or voice, or digital data like perhaps textbooks. The last component required for transmission of these signals is the antenna, and this is such a vast topic that as we said yesterday, we have to give it its own lesson. Antennas mystify even some RF engineers and technicians, myself included, and possibly you for a little while. They're responsible for the marvelous magic of RF communications themselves. The purpose of the antenna is to convert electricity into electromagnetic waves, then radiate or move them away from the antenna at the transmitter end, and then at the receiver end, receive them and pick them up. uh, the field of wireless communications is growing at a very fast pace, and with new standards and technologies being introduced seemingly every week, wireless service providers and retailers, and in fact all kinds of businesses, are beginning to deploy wireless networks everywhere. Hotels, airports, train stations, restaurants, cafes, shopping malls, and even in public parks and other areas. The use of cellular telephones has exploded in ways that uh, few people could ever imagine. Employees in all types of industries are being equipped with smartphones and tablet computers so they can stay in touch through voice and email at all times from anywhere in the world. Antennas play a key role in the successful deployment of any kind of wireless connection. In this lesson, we're going to be talking about uh, antennas and their types and sizes and applications, as well as implementation issues. We're going to learn about power gain and loss. We're going to learn the physical aspects of antennas. Uh, Mostly, we're going to be discussing antennas that are used in a limited range of wireless communication technologies. However, the basic concepts cross over to other RF communication technologies, and the information provided here can be easily extended to other types of antenna systems. So understanding RF signal transmission involves knowing the strength or the power with which the transmitter is sending the signal, the amount of reduction in signal strength caused by the cables or connectors and other components, the transmission medium with electronic waves, and the minimum strength of a signal required by the receiver to be able to properly recover and the data that was sent to the transmitter. Now, these requirements mean that we need to know how much power the signal loses or gains at various points. So, for example, an analysis of a signal would determine the power level that was fed into the antenna, and then how much signal strength was lost in transit from the transmitter to the receiver, maybe because of obstacles or other things that may have gotten in the way. If you consider a wireless cable or DSL router for home networking, which typically sends out a signal with approximately 32 milliwatts or 0.032 watts. The router is on the lower level of the house, and by the time the signal reaches the wireless NIC in a laptop on the second floor bedroom, it may only have a signal strength of 0.0000001, or like 10 to the negative 9th watts, or a nanowatt. Now, with received signals being sometimes several million times smaller than the signals that were transmitted, performing calculations with many digits to the right of the decimal point is challenging. It's easy to make a mistake reading, writing, or typing these long numbers, even with a calculator. Now, fortunately, engineers have had the same kind of difficulty with these very large or very small numbers. So in the 20s, Bell Labs came up with a system to simplify those calculations. So if we recall from previous lessons that an amplifier boosts the power of a signal, and when this happens, that effect is called a gain. Conversely, cables and connectors offer resistance to the flow of electricity and therefore tend to decrease the flow of electricity and the power of the signal. Humidity, dust, and other obstacles like walls and human bodies also cause the signal to lose strength. This effect is called your loss. Now, knowing how much gain or how much loss occurs in our system, composed of radio transmitters, receivers, cables, connectors, and antennas, is necessary to assist RF engineers and technicians in selecting the appropriate components and then properly installing them for reliable signal transmission and reception. It's also important to understand that a signal's power does not usually change in linear fashion. Instead, it changes logarithmically. It's a tough word to pronounce, okay? But it's easier to show. So this graph of two values, okay, one that changes in linear and one that changes in a logarithmic fashion. So gain and loss are relative concepts, which means that you need to know the power level of the signal at two different points, such as the transmitting antenna and the receiving antenna. Relative concepts are best quantified with relative measurements, such as percentages. To calculate the signal loss using percentages for our sample wireless cable DSL router in our home network, you would still have to deal with numbers that are difficult to read, write, or even type. So let's take a look at it in a much easier way to work with gain and loss without losing numbers. And that's decibel, or dB. Now, it's a ratio between two signal levels. A relative measurement, i.e., for example, one in which a value is dependent of another value. That makes it much simpler to express and then calculate power gain or loss. Here's how it gets done. Now, to calculate gain, all you need to remember is, in practically all cases, is that a gain of 3 dB plus 3B, okay, means that the signal is 2 times bigger, or twice the power. So 3B, twice the power. 10B means signal is 10 times the power. Okay? Why 3 is twice and 10 is 10, I don't know. But a loss, negative 3B, means that it's twice as small, or half the power. And the loss of 10B, okay, means the signal is 10 times smaller, or a tenth the power. Now these rules are known as tens and threes of RF mathematics. So as you'll see, you can easily and quickly calculate the gain or loss with a reasonable amount of accuracy without having to use a calculator, such as following these simple rules. Okay? Using dB to represent gains and losses means that the only types of calculations required are simple additions and subtractions. There's no need for multiplication, division, or any other kind of complex calculation to convert the values to the same unit in order to get a meaningful result. So, for example, if the transmitter is connected to a cable that has a loss of 4 dB, and each connector, one on the transmitter end of the cable and one on the antenna end of the cable, has a loss of 1 dB, you can simply add the losses together like so. So we had the loss of force, here your negative 4 dB, plus 1 dB negative, plus 1 dB negative. So we have 6 negative dB for a loss of total of 6. Now, although dB is a relative measurement, at some point we have to make a connection or a reference between dB and linear measurements or absolute measurements. So for the example of this would be what we call a dBm or a milliwatt. Almost dropped my computer. So this is a relative way to indicate an absolute power level in the linear watt scale. So 1 milliwatt equals 0 dBm. You can add or subtract any value represented in dB or dBm using the tens and threes rule. So now you can convert a dBm value directly into milliwatts of power. So let's look at some examples. You got a positive 3 dB, okay, will double the power, okay. So 10 milliwatts plus 3 dB is approximately 20 milliwatts. Negative 3 dB will have the power of 10 milliwatts, so now it's down to 5. A positive 10 dB will increase it by 10-fold. So 10 milliwatts plus 10 dB will make it 100 milliwatts. Or negative 10 milliwatts, or negative 10 dB on 10 milliwatts would be negative 10 dB or 1 milliwatt. Therefore, if you want to know the absolute power of a particular signal that is supplied by a transmitter, and you know from the specifications for this particular unit that the strength of the output signal is plus 36 dBm, and then you calculate the absolute power by breaking the number down. So you have 36 dBm, which is 10 dBm plus 10 dBm plus 10 dBm, because you want to use tens and threes, plus 3 dBm plus 3 dBm. If 0 dBm equals to 1 milliwatt, then adding 10 dB makes the signal watt power, or the signal power, to be 10 milliwatts, or 1 milliwatt multiplied by 10. Adding another 10 dB multiplies it by 10, making it 100 milliwatts. Adding another 10 dB multiplies the signal power by 10 again, making it 1,000 milliwatts, or 1 milliwatt. Now we have to take the threes, so add another 3 dB, doubles the signal power, making it 2 milliwatts. Adding another 3 decibel, doubles signal power again, making it 4 milliwatts. So when assigning a dB factor to the gain of an antenna, the measurement must relate to some absolute value. And the most perfect radiator of electromagnetic waves is an isotropic radiator. It's a theoretically perfect sphere that radiates energy equally in all directions. It is not possible to build a real isotropic radiator because it would need a power and a signal cable connected to it at some point on the surface of the sphere, thus making it no longer perfect. The cable connection means that the sphere would no longer be perfect and would not be able to radiate with equal intensity in all directions. An antenna does not transmit a signal where the cable is connected to it. However, the signal being fed into the antenna from the transmitter circuit does not change. That energy will result in an electromagnetic wave, as well as a slight increase in the energy that did not propagate from the point where the cable was connected to the antenna. This is why antennas exhibit a gain, which we'll talk about later on. Now, as a reference point, An isotropic radiator has a theoretical gain of 0 dBm, 1 milliwatt. Now, antenna gain is expressed using dBi, or a dipole isotropic, or I should write this case here, it's just decibel isotropic. A relative measurement of the gain of the antenna as compared to the gain of the isotropic radiator. For microwave and higher frequency antennas, antenna gain is usually expressed in the dB or dipole. A dipole is the smallest, simplest, most practical type of antenna that can be made and exhibits the least amount of gain. Dipole has a fixed gain of 2.5 dB over that of an isotropic radiator. Therefore, if the gain of the antenna is 5 dBd, to convert it to a dPi, you simply add 2.5 to the 5 and you get a 7.5 dPi. This table shows a summary of the decibel measurements used in RF communication. Now that we have a kind of an understanding of gain and loss, it is time to get acquainted with antenna types, sizes, and their shapes. Antennas used in wireless communications can be characterized as either passive or active. Remember, if it's for adding power to something, it's typically going to be active, and if it's passive, we're not adding any power to it. So passive antennas are the most common type, and they're constructed of a piece of metal, wire, or similar conductive material. Passive antenna does not amplify the signal in any way. It can only radiate a signal from with the same amount of energy that appears at the antenna connector, minus any losses introduced by the antenna cable and connector. However, as you've learned, certain shapes of passive antennas radiate the RF energy supplied by the transmitter in one direction, and consequently exhibit an effective gain that's similar to the amplification of the signal and is called a directional gain. So if we were to look at the graphic here, the light bulb on the left emits light energy all around it, except from the base, much like an omnidirectional antenna. Conversely, if you have a reflector around the light bulb, all the light energy will be concentrated and emitted in one direction. Which then takes us to our active antennas. Now, active antennas are essentially passive antennas with built-in amplifiers. So the amplifiers connect directly to the piece of metal that forms the antenna itself. Most active antennas have only one electrical connection. The RF signal and the power for the amplifier are then supplied on the same conductor. It's intended to reduce the cost and make active antennas easier to install. The active antennas are not common due to their much higher costs. Now, antennas come in many different shapes and sizes, and depending on the following characteristics, such as the frequency that the antenna is designed to transmit and receive, the direction of the radiated electromagnetic wave, and the power with which the antenna must transmit, or even how sensitive it needs to be to receive weak signals. Depending on those characteristics, the size of the antenna is inversely proportionate to the frequency of the signal it is designed to transmit or receive. Now, lower frequency signals require larger antenna. Conversely, higher frequency signals require shorter antennas. So, for example, the antenna of an AM radio station transmitting at 530 kilohertz is 566 feet long, whereas that of a cell tower operating at 900 megahertz, it's just over 13 inches long. Antenna shapes vary according to their specific applications. Now we have an omnidirectional antenna, which is used to transmit and receive signals from all directions with relatively equal intensity. As this graphic shows, okay, there's two examples of omnidirectional antennas. Okay. On the left is a magnetic mount antenna. You see this in like police cars and stuff, with an integrated cable designed for use in wireless LAN applications. When I did work for the police department, we used to keep the vehicle computers were actually in the trunk, and then we would plug that antenna into the computers in the trunk. But since the trunk was too well shielded, we couldn't get a signal out from the air card, so that cable would plug into the air card, and we would mount that in the back of the car, and it wouldn't fall off because it was on there through a very strong magnet. Now they're used to improve the signal reception over antennas that are built inside laptop computers or permanently attached to a wireless network card. Magnetic mount antennas can be used in office environments where they can be easily attached to any metal surface, or they can be attached to the roof of a car or a truck, as I described earlier. On the right is what we call a blister type ceiling mount antenna. Now, these blister antennas are typically used to hide the antenna that is actually on the inside, and it's really just to make it blend in with the aesthetics around it. There is a longer omnidirectional antenna that usually have a higher gain but are more difficult to mount and hide. And we'll talk about those later on, but you're going to learn about how the size of the antenna can also affect the gain. What we're looking at here is a high gain antenna type. Okay, it exhibits these omnidirectional antennas exhibit passive gain because they emit a signal in 2 dimensions only, not in 3, like an isotropic radiator. When viewed from the side, the RF waves from an omnidirectional antenna will propagate from the sides or the length of the antenna, forming a donut-shaped pattern around it and therefore somewhat more focused. We do also have directional antennas. Now, the shape of a directional antenna also affects the intended direction of the radiated waves. So the directional antenna is used to transmit a data signal in one direction only. Although it may sound obvious, it represents an important difference between the omnidirectional and directional. Directional antennas, by focusing the RF waves mostly in one direction, will concentrate the energy in one direction at the transmitter or receive more energy. In the case of a receiver antenna from one direction, this means that they exhibit more gain from an omnidirectional antenna. Now, some types of directional antennas focus the RF energy more or less than others. We have something called a Yagi antenna, which emits a wider, less focused RF energy beam, whereas a parabolic dish antenna emits a narrow, more concentrated beam of RF energy. Yagi and dish antennas are both used for longer distances, your outdoor type applications. And dish antennas are typically used for links of typically 16 miles or more. Dish antennas are used in point-to-point links, each aimed at one another's dish antenna, but Yagi antennas, in addition to being used in point-to-point links, are also sometimes used to enhance signal quality and extend the distance of links to and from an omnidirectional. So there's an example of a Yagi antenna. Now, one common application of a dish antenna, okay, is to receive satellite signals. So here, like this figure here, it shows two different. This one here shows two different models of Yagi antennas. Now you'll see that it is not always easy to tell which type of antenna it is, okay, just by looking how it looks. And then this one here shows what we call a parabolic dish antenna. Now the dish antenna, the parabolic surface of the dish is used to reflect the received digital or received signal onto the antenna element. At the transmitter end, the signal leaving the antenna element is reflected by the dish and then leaves the antenna in one direction only. Then there's something called a patch antenna. Now, patch antennas emit an RF energy beam that is horizontally narrow but vertically wider, or taller than a Yagi antenna. So, considered a semi-directional antenna, it's often used to send RF energy down a long, narrow corridor, although some varieties are designed for installation on the walls of buildings, for example, to send an RF signal in one direction away from the structure where they're mounted. Cellular telephony antennas are also designed to emit signals away from the tower or the side of the building where they're usually mounted. So this example here, it shows the antennas used in a cellular telephone tower. And here's an indoor patch antenna. The signal strength and distance is a big factor. The distance between the transmitter and the receiver determines the strength of the signal that you need to send, which in turn will determine what size and shape of antenna you need for your application. Now, if you remember that most antennas are of the passive type and that the transmitters can only produce finite amounts of RF energy. Well, so for most applications, active antennas can be extremely expensive, and frequency licensing restrictions limit the amount of power with which the signal can then be transmitted. So what is going to be our best solution? Well, an omnidirectional antenna installed high and in a central location works well for sending a signal in all directions, but the strength of the signal is divided more or less equally in a 360-degree circle around the antenna. So the directional antenna, on the other hand, sends most of the energy in the direction that the antenna itself is actually pointed. Therefore, the RF wave travels further than a signal that was sent from an omnidirectional antenna because the power is all concentrated in one direction. So it's an effect similar to like a light bulb that we saw where it had the reflecting dome around it and then it reflects and pushes the light in one direction. Think of like a flashlight. Okay, the flashlight sends the beam out in one direction. Okay. Signals also lose energy as the electromagnetic wave travels away from the antenna. Okay? This behavior is primarily the result of free space loss. This happens because RF waves tend to spread away from the source of the signal, which is the antenna, similar to the circular wave created when you throw that stone into a pond. Further the waves move away from the stone's impact point, the smaller that the waves will get, or the amount of energy that dispersed actually gets as it moves further and further away. If you place two floating objects on a water surface, one near the point where the stone hit, and one further away, the one that's closer will have more ripples from the waves as opposed to the one that's further away, and the ripples will also be further away from each other. Okay. So designing antennas and understanding how they perform this magic of sending the RF signals out into the air or space requires in-depth knowledge of physics, mathematics, and electronics. And the details of the science behind how antennas actually work are more than what we would talk about in this class, and are probably best left for like engineering courses or in RF electronics. However, we do have to cover some general knowledge of basic antenna functionality so we can move along. And the first thing we want to talk about really is wavelength. Okay? The length of a signal or an RF sine wave, known as the wavelength, is what determines the size of the antenna. So an antenna transmits and receives a signal most efficiently at a specific frequency when it is as long as the full length of the wave. So this is called a full wave antenna. In most cases, it is not practical. So for example, a full wave antenna for an AM station might be about 1,857 feet, whereas a typical cellular antenna would have to be about 13 inches overall. For practical reasons, antennas are more commonly designed to be as long as an exact fraction of the wavelength. And these are called what we call half-wave antennas, or quarter-wave antennas, or eighth-wave antennas. Though not as efficient as full-wave antennas, these smaller antennas work well enough to ensure reliable transmission and reception. So an AM station antenna, for example, could be built as a quarter-wave antenna at about 464 feet as opposed to the 1,800 feet, right? Which is still large, okay? And the cellular antenna, using the same ratio, could be 3¼ inches long, which is about the size of your smartphone today. Now, when antennas have a higher gain, with a higher gain required, you can increase the size of the antenna to the next bigger fraction. The larger the antenna larger antenna would exhibit a higher gain than the shorter antenna. Almost any metallic object or any object that conducts electricity can act as an antenna. But if you use an antenna that is much shorter than the wavelength or a particular frequency, it will not radiate any significant amount of radio frequency. Alternatively, if the antenna is longer, much longer than the wavelength, it will send out some RF energy, just not send it out efficiently. And this may affect reliability of the transmitter circuits as well. Now, in antenna design, certain items such as fasteners, brackets, and support structures can affect the way the antenna emits RF waves. Now, during the testing phase of an antenna, engineers will develop a graphic called an antenna pattern by measuring the signal radiating from the antenna. The antenna pattern indicates the direction, width, and the shape of the RF signal that's coming from the antenna. An antenna pattern is usually drawn as if you're looking at it from the top. So in this case, in the case of directional antennas, sometimes you will see an arrow indicating the direction in which the RF signal is then being emitted. So for example, here you can see the antennas, and then you see the arrows going in particular directions to show you the patterns of the beams, or the direction of the beams. So if you remember that antennas emit signals in 2 dimensions, horizontally and vertically, with antenna specifications almost always include a vertical beam angle that a particular antenna would emit. So here it illustrates the shape of an RF waves emitted by an omnidirectional antenna as if we were viewing it from the side. So I have my antenna directly there in the middle, and then you can see how it goes out on each side. You'll notice it doesn't go, it's definitely not going to come down here at the bottom because the cable would stop that, and then it's just too small of a gap here for it to give anything out of the top of the antenna. When a signal leaves the antenna, the waves have a particular orientation, which meaning the oscillations are oriented either horizontally or vertically. The orientation of the wave leaving the antenna is called the antenna's polarization. Now, if you hold a cell phone straight up in your hand, the antenna is actually positioned vertically. It's up and down. Now, the signal leaving the antenna in this case will be vertically polarized, meaning that the sine waves will travel up and down when leaving the antenna. And if you're lying down when talking on your cell phone, the signal leaving the antenna is horizontally polarized, which means the sine waves travel from side to side on a horizontal plane. Cell towers antennas are mounted vertically and send out the signals so that they're vertically polarized. Antenna polarization is important because the most efficient signal transmission reception is experienced when the sending and the receiving antennas are equally polarized. That is, they're both either vertically or horizontally polarized. So if we think about it in another fashion, okay, you'll notice that on the left, the signal is more up and down, okay, which is the way that we typically hold our cell phones. Now, yes, if your cell phone is always lying on its desk, so it's on a desk and it's on its back, then a horizontally polarized antenna would probably be best suited for that. Most add-on USB wireless NICs used in laptop computers that stick out of the side of the computer are horizontally polarized, provided that the laptop computer is on top of the desk or on your lap. The wireless residential gateways that the wireless NIC is transmitting to or receiving from usually have their antennas positioned vertical, which means that the signal is not polarized, not in the same position as the signals emitted or received by the laptop computer. Conversely, the built-in wireless NIC in laptops usually have the antennas mounted on the back of the screen. Different polarization between devices can cause poor communication between them. Utility software supplied with wireless NICs can show the strength of the signal. And if you experience poor reception, try placing your computer on its side, obviously carefully, while monitoring the signal strength. You'll most likely see a small increase in signal due to the antenna having the same polarization. So here you can see we have a laptop computer and an add-on wireless NIC, which is horizontally mounted, with the AP antennas mounted vertically. We have one-dimensional antennas that are basically a length of wire or metal. They can be built as a straight piece or bent in some shape, such as an old rabbit ear antenna that we used to put on top of our TV sets. We have a monopole antenna, which is basically a straight piece of wire metal, usually a quarter of the wavelength, with no reflecting or grounding element. And as we talked about earlier, a dipole is the smallest, simplest, most practical type of antenna. Dipoles are commonly used as two monopoles mounted together at the base, and where the cable will connect to the antenna, and then laid out then in a straight line, and the two ends face then away from each other, kind of like that. A monopole antenna is less efficient than a dipole. Dipoles can be built larger because they're usually laid out horizontally. To work properly, monopole antennas are mounted in such a way that they're practically sticking out of the ground or very close to it, or some other type of large structure that reflects the electromagnetic energy. Because the ground reflects the waves, it acts as a reflector, and this makes the monopole antenna behave like a dipole, rendering it more efficient. Alternatively, a monopole can be equipped with a large metal base called a ground plane to simulate the signal reflecting effect of the ground and increase efficiency. The most common application for ground planes is on like boats that have fiberglass hulls. fiberglass is non-conducting and does not reflect radio waves. Therefore, antennas for nautical radios usually have either a horizontal metal plate near the base or alternatively 4 lengths of wire sticking out horizontally from the base to act as a grounding plane. We also have two-dimensional antennas that are organized in a two-dimensional pattern, which with both height and width, and are known as the two-dimensional antennas. These include patch and satellite dish antennas. Satellite dish works like a signal collector, scooping up any signal that comes in a straight line with the center axis of the antenna. A patch antenna is usually a flat piece of metal with different heights and widths depending on the desired vertical and horizontal radiation angles. Another type of two-dimensional antenna is what we call a horn antenna. Which resembles a large horn with the wide end bent to one side in a parabolic curve. Now, these antennas are common in telephone networks and are used to transmit high-power microwave signals between two very distant towers, usually over 18 miles or more away. Okay. There's also something out there called a smart antenna. Newer development in antenna technology used primarily in cellular and telephony and WiMAX networks. The smart antenna uses the strength of the signal coming from a mobile device, okay, and learn where it's located, track it, focus the RF energy in the device's direction to avoid wasting energy, which also prevents interference from other antennas. So instead of sending signals with wide beams or spreading the energy over 360 degrees like an omnidirectional antenna, smart antennas send narrow beams of energy toward the receiver. As you see, the illustration on the left shows a regular directional antenna, and the one on the right shows a smart tracking or smart antenna tracking, which literally just goes out and finds the mobile device that it's trying to hit. Now, there are two classes of smart antennas. We have a switch beam antenna. And the switch beam antenna uses several narrow beam antennas pointing in different directions, and then turns each one on or off as the receiver moves across the path. There's also an adaptive or a phased array antenna. It's similar to patch antenna, but instead of being just a single piece of metal, it's divided into matrix of radiating elements. So a computer-based signal processor then will control the circuits in the antenna system, turning elements of the matrix on or off, as well as adjusting the phase of the transmission signal supplied to each one of the mobile user, each one as the mobile user moves across the front of the antenna. Okay. This has an effect of sending an energy beam in a particular direction and is sometimes called beam forming. Now, the processor is also able to determine the relative position of the mobile device by calculating its position based on the time difference of receiving a signal in different antennas, as well as the strength of the signal. Okay. Phased array antennas are used extensively in ultramodern radar systems. So, for example, you may have noticed that newer warships have far fewer rotating radar antenna than the older warships do. Now, phased array antennas also use they're also used in aircraft and nose radar systems as seen here, because there are no moving parts to wear out or break. This also makes these antennas a lot more reliable and long-lasting. So this in turn helps to justify the higher cost of the smart electronics in these antennas. So here you can see how a transmitter varies the phase when transmitting the same signal from different elements in the array. It makes the signal arrive in phase at a particular physical location where the waves from different elements cross, which maximizes the signal strength at the receiver itself. Phased array and switched beam antenna, or smart antenna systems, can be used for other applications as well, such as cellular telephony and even for radio stations in areas where interference from nearby radio transmitters operating in the same frequency range is very high. Now, this can happen where large cities are relatively close to each other and the limited frequency spectrum in the area is crowded. However, due to very high cost of these smart antenna systems, these are not the most common systems that we see today. So now we have to implement all these antennas, and the proper installation of antennas requires knowledge of the user's requirements, okay, as well as an ability to deal with various challenges, including, what physical objects are their buildings going to be in the way, what are the building codes, and other regulatory restrictions that may be imposed by our local and state and federal municipalities. Now, as mentioned at the beginning of the lesson, cell providers spend a great deal of time and effort designing and testing their antenna networks in order to provide the best signal coverage and hence best service their customers. Okay? The purpose of a single RF antenna or a system consisting of multiple antennas is to allow a group of users to communicate reliably without the wires. The system's performance and reliability are the major concerns for an RF technician, and so is security. Now, it's especially true today when unlicensed frequencies are often accompanied by maximum signal power restrictions, which is a lack of support from regulatory agencies. Now, when implementing wireless communications, such as when setting up a wireless LAN, using the antennas that supply with the wireless devices limits you to placing the transmitters and receivers where you can achieve a good connection. If you need to go beyond the standard setup, however, if, for example, say you purchase several different external antennas to ensure good signal reception in a difficult area, maybe for an outdoor link, there's a few things that you might want to consider. Okay, most antennas are connected to the transmitter receiver using coax. This type of cable is built in layers of wires conducting and insulators non-conducting. So if we're to take a look at what coax looks like, we don't have one. We've seen pictures of coax. Okay, coax cables come in many sizes and thicknesses. In our system, it's important to use the correct type of cable per the equipment and antenna manufacturer specifications. Among the specifications is the impedance of the cable, which is the opposition to the flow of alternating current in the circuit, okay, which is represented by a Z, the letter Z, and measured in ohms. Impedance is a combination of the circuit's resistance, induction, and capacitance. The cable's impedance must match that of the transmitter circuit as well as that of the antenna. Once again, the cable's impedance must match that of the circuit and that of the antenna. So when you need to connect an external antenna and it is not possible to attach directly to the transmitter output, you must consider the signal loss caused by the connectors and by the cable itself. Also, all conducting materials add a resistance to the flow of electricity on the wire. This is particularly important in antenna cables and more so important in equipment that transmits at such a very low power like those used in our 802.11 wireless LANs. Cable loss is measured in relation to the length of the cable, The longer the cable, the more loss. In RF, you should use special low-loss antenna cables to minimize signal loss. Here you can see a list of low-loss cables of varying thicknesses along with the losses that occur at a 2.4 gigahertz frequency for every 100 feet. Now, to calculate a total cable loss, divide the loss per 100 feet by 100 and then multiply by the required length of the cable. So, for example, if you needed to install an antenna about 10 feet away from the transmitter, you would have an LMR 100 cable, would introduce a 3.9 dB, okay, introduce a loss of 3.9 dB, which is 39 dB divided by 100, which is 0.39 dB per foot times 10. And that means that significantly more than half the energy produced at the transmitter is lost, and that is before adding the connector's losses. So using LMR 400, the loss introduced by the cable would only be about 0.7 dB. So to keep the loss at a minimum, you may have to use a cable that is too thick for the connector type used in your transmitter antenna or even both. The first consideration when deciding to change the manufacturer provided equipment, mounting antennas and locations, is the loss. In addition, you should be aware that LMR cable is significantly more expensive than regular coax. It easily consists of costing 10 times more in price. So the way that radio waves propagate or move between the transmitter and receiver through the atmosphere of our planet depends on the frequency of the signal. RF waves are classified in 3 groups. Okay? Ground waves, okay, which follow the curvature of the Earth. Sky waves, which bounce between the ionosphere and the surface of the Earth. And RF waves transmitted in frequencies between 30 and 300 require a line of sight between the antenna pair. In most wireless communication applications, one transmitter communicates with several mobile clients, and this is called a point-to-multipoint wireless link. If the receiver is installed in a fixed location, as in the case of, say, a central building in a campus, with wireless links to other buildings, it is possible to maximize the performance of an RF link by using an omnidirectional antenna at a central location, or a directional higher gain antenna at the remote. So as you can see here, the building 1 is just pushing out in all these different directions, right? But then building 2, 3, and 4 have a dish, and that is allowing them to more focus the signal into the receiver. Okay, 2 computer networks on point-to-point links. 2 computer networks in different buildings can be connected by a point-to-point link. In this case, directional antenna provide that most reliable method for transmitting RF waves. The narrow beams and high gain will ensure that most of the energy of the RF wave will be used between the 2 antennas. The cost is often much lower, and the performance is comparable to or higher than that of a directional telephone line. Okay? Telephone companies make extensive use of point-to-point microwave links instead of cables for long-distance voice and data. Although repeater towers are required, the cost of maintaining a wireless link is usually much lower than the cost of installing and maintaining cables, which could be easily damaged, and many times it's just very difficult to troubleshoot. Next thing we want to discuss is something called a Fresnel zone. Okay, now although the transmission path for point-to-point links is usually represented by a straight line, recall that RF waves have a tendency to spread out. Now this means that the space between the 2 antennas should be more accurately represented by something similar to an ellipse. Now, the elliptical region is sometimes called a Fresnel zone. Okay, and its shape is an important consideration in wireless links. Okay, so when planning a wireless link, you have to understand that at least 60% of the Fresnel zone must be kept clear of the obstructions, which may affect the height of the antenna tower. If an obstruction such as a tree or a building blocks more than 40% of the RF signal, it blocks the radio signals completely. The Fresnel zone is sometimes referred to as an RF line of sight and is far more critical than a visual line of sight, meaning that although a person is standing next to an antenna may be able to see the other antenna, the transceivers at the either end of the point-to-point wireless link may not be able to communicate because of having more than 40% of the signal being blocked because of how it expands outward. And when it comes down to everything, okay, once you've considered the cables, the antenna types, the link type, the Fresnel zone of your transmission, you need to calculate whether or not you're going to have enough signal strength to meet the receiver's minimum requirements. This is called a link budget, and it's used in every type of outdoor wireless link, whether across the road or between a satellite or an earth station. The process involves all the variables that you have read in the book and that we've talked about today. The calculations are not very complex, but there are many factors that you must consider. And one of the simplest ways to calculate a link budget is to download a spreadsheet or a tool that is available on the internet at little or no cost. And to calculate your link budget, you'll need information from the equipment specifications, including the gain of the antenna, cable, connector losses for the receiver, the transmitter, receiver sensitivity, and the free space loss figure. One of the challenges of implementing a point-to-point link is to position the antenna at the same height and point them toward one another to maximize the strength of the signal. Recall that you have to ensure that a minimum of 60% of the Fresnel zone is not blocked by obstructions. The height at which the antenna will be mounted can be affected by trees, buildings, curvature of the earth. Some transmitters and receivers are equipped with tools designed to assist the installers in aligning the two antennas. Others may require the rental or purchase of additional tools to ensure perfect alignment. Some basic tools are essential, such as a compass to position the antenna in the correct direction, a spotting scope or binoculars, a means of communication like a walkie-talkie or a cell phone so you can talk to the person on the other end aligning the antenna, a light source such as a flashlight or a laser pointer if the distance is relatively short, a topographical map, a graph that shows elevations and ground, or some way of determining the height of a building or tower where the antenna is to be mounted. Technicians who perform long-distance link installations and who need to align antenna with a great degree of accuracy to ensure maximum reliability are usually equipped with some type of spectrum analyzer, such as, do we have it? No, we don't. There's one in your books. There's one in your books on figure 424. And the tool displays the signal amplitude and bandwidth used by the signal, showing a graphic of the signal in the frequency domain, instead of an oscilloscope, which displays a signal in the time domain. Spectrum analyzers can also display interference happening in a particular frequency channel and offer multiple display options, and they're pretty expensive, typically running anywhere from $10,000 to $100,000, depending on the frequency ranges and the features that you're looking for. Okay. Antenna system implementation, including alignment and troubleshooting, demands hours of practical training, although it is beyond what we're going to be talking about in this class. Before moving on to other more practical aspects of wireless communications, we need to talk about some other challenges that would affect implementation. Some of those are outdoor links. Radio waves can reflect off. They can diffract or be absorbed by other various materials. Weather, such as heavy fog, rain, dust, snowstorms, or air disturbances such as air masses rising quickly from the ground because of the sun heating up a surface in deserts or other hot areas. Significant drops in temperatures that occur in deep valleys during the course of a day. All this can affect the performance and reliability of a wireless link. Seasonal changes can also impact a wireless link. For example, if you say it was set up in the winter when there were no leaves or trees, and then spring arrives, the leaves grow in, and now you've blocked out 40% of your Fresnel zone. Okay? When planning an outdoor link, you should always consider the possibility that the link performance will be seriously affected, or the link will go down completely as a result of one of the environmental conditions that we talked about. You want to check the history of the region's weather, contact municipal planning, parks, building permit departments to identify if there's going to be any short or long-term projects going on in the area that might affect whether or not you're going to have a point-to-point or multi-point-to-point link. The possibility of another company or a person setting up a link in your area, which could interfere with your radio frequency, could be a concern. If you're using unlicensed frequencies such as ISM or unibands, you can't count on the assistance from regulatory agencies or authorities. So of course you always got to be ready for someone to make sure that you're not interfering with anyone else's signal before you set up your outdoor link. Okay. And that concludes our lesson on Chapter 4. Antennas are a big deal, and I'm sure some of you have even set up something as simple as your own home networks have deal with antenna issues or range issues. Myself with dealing with I tested out numerous mesh systems in my own home, and I found out that some systems just worked better, and it had a lot to do with where we place our satellites and where we place our antenna. So with that, stay tuned. We'll have Chapter 5 coming to you shortly.